Hello and welcome to all students. In the previous lecture, we saw how to find integrating factor or integrating factor by inspection, and how to find the differential equation by using a method uh, by integrating factor by inspection. Now, the in this lecture we solve in this lecture we study the determination of integrating factor, and we will solve the problems based on it. Let us see what progress can be made on the problem of determination of an integrating factor for the equation mdx plus ndy equal to 0. Suppose suppose that u, possibly a function of both x and y, is to be integrating factor of first, then the equation u mdx plus u and dy equal to 0 must be exact differential equation. Therefore, by the result of section 10, partial derivative of um with respect to y and partial derivative of un with respect to x, they are same. Hence, you must satisfy the partial differential equation u dou m by dou y plus m dou u by dou y is equal to u dou n by dou x plus n into dou u by dou x. Or we can write this differential equation like this: u into dou m by dou y minus dou n by dou x is equal to n into dou u by dou x minus m into dou u by dou y. Furthermore, by reversing the arrangement above, it can be seen that if u satisfies equation 3, u is an integrating factor for equation 1. We have reduced the problem of solving the ordinary differential equation 1 to the problem of solving a problem of obtaining a particular solution of a partial differential equation 3. Not much has been gained because we have developed no method for attacking on equations such as 3. Therefore, we turn the problem back into realm of ordinary differential equation by restricting u to be a function of only one variable. First, let u be a function of x alone, then dou u by dou y is equal to 0, and dou u by dou x becomes du by dx. Then 3 reduces to u into dou m by dou y minus dou n by dou x is equal to n into dou u by n into du by dx, or 1 upon n dou m by dou y minus dou n by dou x dx is equal to du upon u. So this is equation 4. In the left member of the above equation is a function of x alone, then we can determine u at once. Indeed, if 1 upon n dou m by dou y minus dou n by dou x is equal to f of x, this is equation 5, then the desired integrating factor is u is equal to e raised to the power integration f of x dx. By a similar argument, assuming that u is a function of y alone, we are lead to conclusion that if 1 upon m 1 upon m if 1 upon m dou m by dou y minus dou n by dou x is equal to conclusion that if 1 upon m dou m by dou y minus dou n by dou x is equal to gy, then an integrating factor for equation 1 is u is equal to e raised to the power minus integration g of y dy. So our two results are expressed in the following rules. If 1 upon n dou m by dou y minus dou n by dou x is equal to f of x, a function of x alone, then e raised to the power integration f of x dx is an integrating factor for the equation m dx plus n dy equal to 0. And if 1 upon m dou m by dou y minus dou n by dou x is equal to g of y, a function of y alone, then e raised to the power integration e raised to the power minus integration g of y dy is an integrating factor for equation 1. So for equation 1, it should be emphasized that if neither of the preceding criteria is satisfied, we can say only that the equation does not have an integrating factor, that is a function x or y alone. For example, the student should show that the above criteria fail in the case of equation example A. Okay, and here there are some examples which we will see in the next lectures. So let us stop here.